Hopefully, you are already very familiar with place value. That's the idea that we can use the same digits in different locations within a number to represent larger and smaller quantities. While place value is incredibly useful, there are limitations to how well it can represent very large and very small numbers. In fact, if you are a scientist, you would quickly discover that you are working with numbers too big or too small to be worked with conveniently using regular place value. Well, it's for that reason there's a different system of writing down numbers called scientific notation. The decimal number system, the number system we use every day, is base 10, which means each place value corresponds to a different power of 10. So if a number n is positive, then 10 to the power of n is 1 shifted n places to the left. And if the value n is negative, then 10 to the power of n is simply 1 shifted the absolute value of n place values to the right. So if we have 10 to the power of 5, that's 1 shifted into the 5th place value to the left, which is 100,000. 10 to the power of negative 4 is 4 places shifted to the right, or 1/10,000th. And 10 to the power of 3 is 1 shifted 3 place values to the left, which is 1,000. We can also use this concept to write certain numbers as a power of 10. So 1 millionth is 10 to the power of negative 6 because it's 6 place values to the right. 10 million has 7 places to the left, so that's 10 to the power of 7. And 1/100th has 2 places to the right, so that's 10 to the power of negative 2. Now notice in each of these examples, the power of 10 was much more concise to write than writing the either very large or very small number. There's a big limitation here though. It only works if there's a 1 in one place value and every other place value is 0. We need something that we can use to represent any large or small number. So scientific notation is a way of writing numbers which uses leading digits multiplied by powers of 10. The leading digits always have a single non-zero digit before the decimal point, with the power of 10 used to shift the place value. Scientific notation with positive powers can represent very big numbers, and scientific notation with negative powers can represent very small numbers. So let's look at some numbers written in both scientific notation and ordinary decimal notation. Now, if you look closely, these examples use the same place value shifts that we did in the previous example. So compare our answers here to the examples we did above. So 7.482 times 10 to the power of 5. We need to shift that 7 into the 100,000s place. So that's 748,200. 5.213 times 10 to the power of negative 4. We need to shift our first digit, 5, in the 10,000ths place, which is 0.0005213. 3.9742 times 10 to the power of 3 means we have to shift our first digit, 3, into the thousands place, which is 3,974.2. Now, more conveniently is taking our either very small or very large numbers and writing them in scientific notation. So this number has its first digit in the 6th place to the right. So this is 3.58 times 10 to the power of negative 6. This number has its first digit in the 7th place to the left. So this is 3.491 times 10 to the power of 7. Notice we don't need to write down all those trailing zeros because they were originally there just to show the correct place value. But we don't need them to show place value anymore. That's what our power of 10 is doing. And this number has its first digit, 8, in the 2nd place to the right. So this is 8.82 times 10 to the power of negative 2. Now, as mentioned above, correct scientific notation only has one digit before the decimal point in the leading digits. So 12.3 times 10 to the power of 8 is not valid scientific notation. Instead, we should write it as 1.23. So really, 12.3 is the same as 1.23 times 10 to the power of 1. It's been shifted over one place. Multiplying that by the 10 to the power of 8 we already had, we get 1.23 times 10 to the power of 9. 0.0234 is the same as 2.34 times 10 to the power of negative 2. Multiplying that by the 10 to the power of 5 we already had, in correct scientific notation, this is 2.34 times 10 to the power of 3. Now the exponent on the 10 is sometimes called the order of magnitude. To compare two numbers in scientific notation, we should compare the order of magnitude first. If these are the same, the numbers have similar size, so now we compare their leading digits. For example, which is larger of 7.452 times 10 to the power of 6 and 3.529 times 10 to the power of negative 2? Looking at their orders of magnitude, 10 to the power of negative 2 is much larger than 10 to the power of negative 6. So, that second number is the larger one. Since we are dealing with scientific notation, let's look at an actual scientific example. So we want to compare the size of a bacterium with diameter 1.5 times 10 to the power of negative 6, a virus with diameter 4.5 times 10 to the power of negative 8, and a red blood cell with a diameter of 8.2 times 10 to the power of negative 6. So we start by looking at the order of magnitude. Both the bacterium and red blood cell are comparable because they have the same order of magnitude. The virus, on the other hand, with 10 to the power of negative 8, is much smaller than the other two. Now, of the two larger ones, the red blood cell is larger because 8.2 is greater than 1.5.